energy and momentum are related to each other.
Yeah.
That's why on the right hand side of the field equation, Einstein's field equation, you have energy, momentum, stress, tensor, whatever, pressure as well. But pressure, I think it comes out of all these things, energy and all, but mass, energy, momentum are related. Like in Newton's world, they are not related.
Yeah, right.
Einstein's
right.
special relativity, these are all related, and so that's why in Einstein's field equation on the right hand side you have energy, momentum, tensor, because they are basically related to each other. So according to him, they should all affect the geometry because they are one and the same. And force is basically momentum with respect to proper time. And I think this is important. So if you start with this same thing, this is the energy, momentum, and all relation. You know that, but then you say Minkowski metric momentum equal to mass square Minkowski metric velocity. It comes from this. You substitute
Right.
momentum.
Okay, that makes sense.
And this we showed is c square. This is c square. We already showed that. So basically P nu, which is equal to E by C, energy by C, P. So this thing. So now this is first. Now if you again use this, and if you use this, you will see P square by C square minus Px square minus Py square minus Pz square. This, if you multiply, which is equal to P square by C square minus the total P square. So if you bring the minus sign out, this is multiplication, like E by C into E by C, Px into Px. And this metric makes sure only the diagonal elements will be. So this is the second equation. So these both are same. So E square by C square minus P square equal to M square C square. So E square equal to P square C square plus M square C raised to 4. This is the actual equation.
Yeah, and I remember seeing that in a physics class. You know, this was but they didn't get it. You know, it was just handed. They didn't explain where it came from.
So where it comes from is this is momentum.
Yeah, so this is nice.
Yeah.
I mean.
So 4 momentum is equal to 4 velocity. You use this mv basically. Then you use this, like if you have. You take that metric. This is like the distance, but for momentum.
Yeah.
And then you use. But I think you need to know. You need to derive through it because you need to come to momentum.
Yeah.
So you need to start with 4 velocity. Then you need to show what is 4 momentum. Then you need to show that this is equal to c squared, and then you get it. So this is the actual equation. E equal to mc square is a short, like it's a special case.
Yeah, right.
But if v is not equal, if v equal to 0, then E will be equal to mc square. But here for light, E comes out to be Pc.
Yeah, and that's nice because
0.
from this, it works for a photon.
Yeah.
You know, and so you don't have to have the other special arguments because usually they have a kind of a lot of hand waving about why the photon. But here
this is for photon.
It comes right out of the equation.
So this is for photon and this is the momentum. So if you want to see what's the momentum of a photon, then it's E by C.
Yeah.
For photon. For light, this is true.
Yeah.
And for everything else, if there is a V, if it's at rest, it's mc square. This is actually mass, rest mass, which doesn't change. Like we say that mass changes if it's at a velocity,
Yeah,
but it's
so
actually the energy which is.
he, like most of the other books I've got, they just say forget rest mass. It's just mass. Mass is a scalar, and that's it. You know. So I think
they're related anyway, so it doesn't matter. I think.
Yeah.
But the rest mass doesn't change. I think the rest mass. The way I look at it is rest mass is a condensed form of energy somehow. I don't know how it condensed.
Yeah, I think once upon a time, historically, people talked about relativistic mass and they had the mass changing. But I think now they don't do that. They just decided to consider mass as mass, and momentum changes, energy changes, but we just keep mass as just a scalar.
I mean, if it at velocity 0, I don't know, now everything is relative, but if you consider it's at rest, and its mass is 0, then it's mc square, m0 c square. And if it's at some velocity, as you are saying, the mass that we see, the increases because of energy, and mass are related. So.
Well, I mean, the thing is, you could say that the mass is increasing, or you could say that the momentum is increasing. Yeah, I mean,
the energy is increasing.
Yeah, the energy is increasing. So I think mostly people have chosen just to take mass out of that equation and just consider it mass is just an invariant.
Yeah.
And just let the change go into energy.
Yeah. But we should also look at this in more detail, I think, when we have time, because I don't know, like mass is because of energy. I mean, I don't know that because of length contraction, I think. Time dilation, I think maybe it's fine, but is length, that Lorentz contraction, is it real or is it just what we see? Is it real or is it just since we are at a different velocity, we feel that time is slow, we feel that the length, because if we rotate something at a high speed 7 colors, we will see it as white. So is this like what we see, or are these formulas real? They should be real because this is not for human perception.
Yeah, so I think they should be real.
Yeah.
They should be real.
But still, we should look at it in depth.
But real doesn't. But it doesn't mean that. It doesn't mean that anything changed.
No, I mean
it just means that we're.
For example, if he is traveling at a high speed, the time will slow down for him. But what we need to look at is it's all related to speed of light. Like imagine that speed of light is not constant for inertial frames and all. I mean, everything is somehow related to C. I see.
Everything
time,
is somehow related to
energy,
C. Yeah.
That's, especially time is somehow.
I still find that very mysterious. Yeah. I find that very mysterious, and like you said, you don't hear enough people talking about that.
Yeah, philosophical implication. What does it mean? Like time is related to C. How? I mean, it's related. It's fine. So how I see is like, even when I come to gravity, I will tell you. Like these are all equations that he gave us, but we don't know what's really happening. Like he looked at it like, okay, speed of light constant. Let's come up with some equations. Like he assumed those two things. Let's see what falls out. These things came out, which is better than what it was earlier. Like Lorentz and all, they were going in a very different direction. They were using ether and all.
Yeah, and they were really talking about contraction was really physically something changing.
But they were also using ether for some
the
special
ether
frame
was
of
pushing.
reference.
The ether was pushing on the thing, and
so this is better.
It's better.
Yeah, much better. But yeah, that is another discussion. Yeah. So now it's manifolds. I think from this discussion, maybe I should just write these two things here: gamma 1 minus b square plus c square, and e square b square c square plus m square c raised to 4. So introduction to manifolds. So matter and energy curve space-time. So, and space-time can be modeled using a mathematical structure known as pseudo-Riemannian manifold. And gravity in general relativity therefore ceases to be regarded as a force, but rather as a property of the geometry of space-time. So pseudo-Riemannian, I think it's almost Riemannian. The reason they call it pseudo-Riemannian is the
Just the minus sign.
minus.
Yeah.
The Riemann manifold and metric. So in order to be able to model the space-time of general relativity, a manifold must also have these two additional properties. So it must be differentiable. When we look at the transformation properties of tensors, it involves a lot of partial derivatives. So basically it should be differentiable,
Right.
and it must be endowed with a symmetric metric tensor. So the metric tensor should be symmetric. G equal to G for general relativity.
Right.
So then I saw, like I was talking to about Kaluza-Klein theories and all, like they were trying to combine electromagnetism and gravity.
Okay.
Later on unified field theories that they were trying. So I saw one approach by Hermann, I don't know what is some surname, Weil, W-E-Y-L, Weil or someone.
Oh, why? Yeah, I don't know how you pronounce it, but Herman Weil. Yeah, I know who you mean.
So he tried using this metric tensor is not symmetric.
Oh.
And let's see if electromagnetism comes out. That was one of the approach. Another approach was increase one of the dimension, go to fifth dimension and see what happens. Those are two approaches that I saw by Kaluza-Klein and Hermann Weil. So a manifold that is differentiable and possesses a symmetric metric tensor is known as Riemann manifold. So a Riemann manifold is differentiable and possesses a symmetric metric tensor.
Okay.
And Riemann discovered that the metric contains all the information we need to describe the curvature of the manifold. Right. If we know the metric, we know the space. And I think in this case we know the space-time. That is why metric is crucial to general relativity. And in n dimension, the Riemann manifold has a line element B L square is G I J D X I D X J. And then summation convention that I goes from whatever dimensions you have. And if metric coefficients are plus or minus 1, then it's a flat space time. And Riemann curvature tensor is absolute acid test for determining whether manifold is flat or curved. If it's all zero at all points, it's flat. Like we can't just look, yeah, this is also flat, but Riemann curvature tensor is the absolute acid test. And if tensor does not equal to 0 at any point, then it's curved at that point. And there are two curvatures, extrinsic curvature and intrinsic curvature. So extrinsic curvature is seen in relation to an external space of higher dimension. Like you can look at a sphere and from in this dimension and say, and intrinsic is by examining directly using metric and mathematical tools derived from metric to analyze their internal structure. I mean, I think this in itself is a big topic.
Yeah, that's a big deal. Yeah.
So in future we need to look into it in details. Then space-time could be modeled using pseudo-Riemannian manifold. They differ from Riemannian manifold, it's negative. dl square can be negative. Then surface of a sphere, I think I should write it down here, we'll keep on using it. So dl square is dr square plus r square d theta square plus r square sine square theta d phi square. So if r is constant, then it's r square d theta square plus this. And in that case, I mean you know that right, r square, the metric tensor will be, just write it down. G I J B r square 0 r square sine square theta. Now space-time manifold is a stage on which the theatre of relativity is played out. The main actors who perform are mathematical objects known as scalars, contravariant vectors, one-forms and tensors. These are the main things. So then the part 5 is scalars, vectors, one-form, tensors. So in general relativity, each vector is located at a single point in space-time. In fact, each point in space-time is itself a vector space and home to infinite number of vectors.
Sorry.
Yeah.
So the top line is from a three-dimensional, right?
Yeah, if you consider R is constant, then this term will go away.
Yeah.
Yes,
Okay.
correct.
Yeah.
So in GR, the vector space will be both the tangent space, contravariant vector. So generally tangent is contravariant and cotangent is one form, that is gradient basically. That's what. So contravariant vector. So there are, yeah. So we were discussing contravariant and covariant last time.
Right.
So contravariant vector, think of a tangent vector to a parameterized curve. That is, like if you have a curve and think of a tangent at every point or something, it's a contravariant vector. The covariant vector, think of a gradient of a scalar field. And so it's gradient of a scalar field. So yeah, those are two other things. So divergence, if you see, is like the flow. Divergence is like if you want to, gradient gives a change, like at that point locally maybe the maximum change or whatever,
Yeah.
according to the function, but gradient gives you the slope sort of, and divergence gives you the flow. Like if it's negative, then it's a sink, or like it's going out, or positive it's going out, negative it's a sink, it's coming in. So it's like a divergence. Then we will see later how a metric tensor is used to convert a vector to its corresponding one form and vice versa. I will just drink some water.
Yeah.
I'll just pause this maybe.